Yeah. Because it's too small.
Can you hear me? Okay. All right. Hi, everyone. My name is Arun. I'm a fellow this semester at Simons, and I'll be talking to you about some cool work I've done on sparsification via a bunch of nice techniques. So what's the plan for the talk? I'll talk briefly about everything I tend to work on, the things I like to think about in theory, some background on the problem, and then I'll talk about the results we have in this talk. And then hopefully we'll have some questions, although I think people want to get to break. Right. There's two broad camps of like what I tend to work on. It's going to be a mixture of convex optimization and fast graph algorithms. But instead of thinking of them as sort of disjoint sets, I think a more useful way of like organizing my general research portfolio is a spectrum. I have on one side hardcore convex optimizations, such as like using higher order methods for better structured convex optimization, semi-definite programming, regression, all the way over to like Laplacian solvers and graph sketches, which are very traditional graph algorithms, I could say. So what I'll be talking about in this talk is something in the middle. It's going to be something maybe everyone in the audience can understand and might find interesting, and it's going to be new approaches for sparsification. So if any of you went to the boot camp, you might see Touchant's version of sparsification, which is like graph sparsification. In this talk, we're going to be talking about something a bit more general. So we have like sort of a meta problem. We have some well-behaved objects, O1, O2, O3, and our goal is we want to find some non-negative weights, where most of them are 0, such that the collection of reweighted objects satisfies some property of the original. It preserves something useful. So in this talk, the version I said in the previous slide is quite general. It recovers a bunch of things, not just sparsification. So the version I'm going to be talking about in this next few slides is the following. Instead of having objects in general, I have functions, O1x, O2x, etc. So these, for example, could represent edge Laplacians or hyperedges, quadratic forms, or even arbitrary norms. And our goal is to find sparse weights which preserve the sum of these objects for all x. So if you think about this, this sort of resembles the version of sparsification that works for graphs. And in fact, like because OI is a very general object, it's an arbitrary function, this notion captures a lot more stuff than you could get with just graph sparsification. So why is this problem interesting? Why do we need this full generality? It actually captures a bunch of interesting cases that are both useful in algorithms and also like theoretically nice. So several of these things are useful in algorithms, like graph sparsification, matrix turnoff. Versions of this are good for approximate regression. And many open questions as to like when this is possible. Like the TCS toolkit, the thing I learned in grad school, don't solve most of the things that I'm going to be talking about in this class. You need to introduce some new ideas. And hopefully you'll find the results cool. All right, so as a quick warm-up, I'll talk very briefly about graph sparsification again. So in graph sparsification, we have some dense weighted graph, and we want a sparse reweighted graph such that the reweighted sparse graph is approximately the dense graph. So we can map this directly onto the notion of sparsification described. We treat every edge Laplacian as a function by like interpreting it as its quadratic form. And our goal is to find a reweighting of these edge Laplacian functions, which is a graph spectral sparsifier in this sense. Where, of course, that notation there refers to like semi-definite ordering, which is exactly equivalent to the notion I described earlier. Right. So as we saw a couple weeks ago, random sampling works very easily to get basically the right bound for this. You can get n log n over epsilon squared size sparsification by just sampling edges randomly. One question that might be interesting is, can you generalize this beyond matrices? Like this works for graphs, it works for matrices more broadly. Can you make this work for anything else? So you might think that you could do some Chernoff style argument. The main issue with this is that this whole approach requires linearity very strongly. So you really need something new. So let me talk about the most general result in this collection. So let's have some collection of n1, n2, n3 being just some semi-norms. So semi-norms are convex functions which have this linear scaling property. And our goal is to find some sparse weights which approximate this sum. So it's a very powerful primitive, and it immediately recovers a bunch of results from the modern TCS literature, like graph cut sparsification, hypergraph cut sparsification. And in fact, you can use this to sparsify sums of symmetrics of budgeted functions, which is a problem that's been studied quite a lot by, I think, a completely different community. So a very slight modification of this also gets you spectral sparsifiers. So this is a very, very general set of techniques. The main obstacle, though, like it's great if we could get this. The main issue is that this is super duper nonlinear. Like, with a matrix, you can sort of like imagine, a matrix as being some sort of linear operator on space. Arbitrary convex functions can do all sorts of weird things. So any sort of analysis that you might want that uses this linearity just immediately falls short. So we need something completely new. So if we actually developed this completely new thing, and we actually got this main result, which says that you can get sparsifiers of near linear size, basically up to log factors, the same as you could get for graphs, for norms as well. And you can get exactly the same notion. The algorithm is also very sort of conceptually similar. It's essentially sampling by some probabilities and reweighting. You essentially sample by this weird probability to find this expected value. And as a very very brief one-sentence summary of what we actually did, we just basically combined an approach based on something called chaining, some clever tricks, and surprisingly, bounds in the KLS constant appear. That's sort of the appearance of the 3.5 and why it's not 3. So that's our main result for this talk. But we actually have some other things that we could have done. So the result I said is sort of stated out of order. We started with this problem called hypergraph sparsification, and then sort of stumbled on norm sparsifications as a result. But hypergraph sparsification is interesting in its own right. So here our functions are these hyper-edge energy functions. So it's like the maximum squared pairwise difference for any UV and belonging to a hyperedge. And this directly generalizes spectral graph sparsification. Like if every hyperedge is size 2, there's only 2 choices for U and V. And clearly UU and VV both give 0. So this is like sort of an interesting problem personally for me. Like it's been studied in TCS for maybe 10 years now. But I personally find this an interesting problem because it's sort of the easiest hard case for the standard toolkit. Like we have things that work for graph sparsification, both spectral and cut. But all of those sort of approaches don't work for hypergraphs, even though they're very, very closely structured to actual graphs.
So is the square root of this the semi-norm?
Yes. So that's sort of what I was saying. This result gets you hypergraph sparsification in the full sense. Yes, if you take the square root of this, that's precisely a semi-norm. Good point. But yeah, that's our main result for hypergraph sparsification. We actually managed to prove a better bound than we could get in general for hyperedges, for hypergraphs, where every hyperedge is small, size at most r. You can find these weights which have this many non-zero entries, which, as you might notice, is like only a log r factor away from what you could get for graphs. So for r constant, this exactly recovers the bound you get with matrix Chernoff up to some universal constant. And very interestingly, this algorithm, you could recover like a version of this result via our sparsification of norms paper, but the algorithm that gets you this tighter bound is completely different. Like the sampling probabilities are like essentially leverage scores of some graph. They're like totally different. So I personally find it an interesting question why you can do so much better for this problem of hypergraphs with such a different set of weights. And again, like the proof's hand wave is basically you just combine an approach based on generic chaining with an analysis based on growth functionals. Just a bunch of math. Okay. So now for something pretty different. I'll go back to matrices for a second. So if you remember with matrix Chernoff from Sushant's talk, you have sparsification with n log n over epsilon squared edges. Great. It turns out, though, that surprisingly, this is not tight. You can do better. There's this paper by Batson, Spielman, and Srivastava, who's in the audience, which gets you this bound of n over epsilon squared. So you can save this log factor, and this turns out to be the right answer. So this is sort of an interesting existential point, but maybe there's a question, can you find these efficiently? And can you find sparsifiers of this quality in some restricted settings? Like let's say I enforce, all the degrees of my graph have to be preserved. What can I do? So the previous work for this problem, this has been studied, finding these linear size sparsifiers in good time. And most previous work follows a very basic template of just trying to find some edges to add to a sparsifier a few at a time. So the original paper added them one at a time. Some work later found that you could add basically root n edges at a time. It's been pushed down. Our setup is completely different from this. Instead of adding edges to a sparsifier, we basically decide to partition the graph. We reduce an m-edge graph to a 0.99 m-edge graph, sort of a reduction by a constant factor. And the ideas we sort of use for this are strongly borrowed from this thing called constructive discrepancy theory. So what do we do? If you remember the problem of constructing a sparsifier, we want LG and LH to be spectrally close. If we sort of reweight every edge in G by this factor of 1 plus XE, sparsification is just equivalent to this matrix here being small. And so it suffices for our main goal of finding some vector X where most of the entries, or only a constant fraction of the entries are equal to -1. Most of the entries can be anything, but if maybe 1% of the entries are small, equal to -1, then applying this to form LH means that you've deleted 1% of your edges from your graph. And there's a theorem you can prove that the set of small x, small in the sense that the spectral norm being small, is large. Large is a technical term here. So given this, we actually have a nice result that says if I have a large set, I can find a point which belongs to K and the hypercube where many entries are equal to -1. So this is exactly the goal I want. The whole question now is finding this. So the algorithm for this is just some fairly complex convex optimization problem. And our main idea is that you can solve this problem approximately, and that gives you something good enough. It turns out the objective function for this is strongly convex. So if I just solve this to some approximate error, I know there exists a point, a minimizer, which has many tight constraints. So my approximate minimizer has many near tight constraints, and I can round this quickly. And this is essentially good enough to make the argument work. With this, we actually improve upon previous work by a quadratic factor. We get linear size sparsifiers in time m over epsilon to 3.5. Previous results were m over epsilon to 6.5, considerably worse. I think you can push this down even further. And also, more interestingly to me, you can actually show that this whole approach tolerates linear subspace constraints. So in particular, you get this thing called linear size degrees preserving sparsifiers, sort of a stepping stone along the line to directed sparsifiers for directed graphs in almost linear time. And this is very nice because the previous state of the art required some polynomial time and didn't even get n over epsilon squared size. So finally, I'll conclude with some future directions, some things I find interesting. If you remember from earlier, there's this whole thing where sampling hypergraphs, there's two completely different set of weights which work for this. You have this weights that are defined from the sampling sum of norms, the sort of expectation of something. And then I claim there's something completely different that also works, gets you a better bound, but it's based on some sort of reweighted leverage score business. Is there some sort of unified theory that works for this? Also, can you get linear size sparsification outside of matrices? We have all of these tools which lose log factors. Can you get something beyond that works for things other than graphs or matrices? Finally, can you sparsify asymmetric objects? Everything in this paper, everything in this talk require origin symmetry of all the things. And finally, can you use this for more algorithmic things? Do you really need just to have this as an existential thing? Can you use this as a subroutine in something that's hopefully fast? That's all I have. Thanks.
Thanks a lot, Arun. Any questions? Yeah, I have one question. So in the Laplacian setting, sparsifiers were useful as preconditioners for Laplacian systems, minimizing Laplacian quadratic form in a subspace. Is there something analogous here? Can you use these? Is there some notion of preconditioning for some optimization problem?
In some work that's hopefully coming out very soon, we can actually use some stuff related to sparsifying sums of norms for improving algorithms for regression.
Oh, okay.
So it is possible. It just is not directly applying sum of norms. You need some tricks.
Any other? So you said that these two approaches give different probability distributions. So and you can do, even in the case of graphs, I guess, you can do this iterative like version of sparsification. Does that distribution, is that related up to constant factors to the leverage score distribution?
So it turns out that in graphs,
Mhm.
both distributions are exactly the same. They're
Uh-huh.
both exactly leverage scores.
Yeah.
Like it turns like
Mhm.
whenever there's some sort of nonlinearity, they sort of become quite different.
Uh,
Like in hypergraphs, you can sort of get away with some reweighted leverage scores. For more general things, where like the norms has a bunch of like faces, if you treat it as a polytope, that approach doesn't work, but some completely different approach does. But the weights are, I think, inherently different.
uh-huh. Okay. Well, thanks a lot, Arun. So we have a break now, and we'll meet again at